Okay, so welcome everyone to this workshop series that this is the first session of, and this series will concentrate on how you can run quantum chemistry calculations with Python. It'll be generating molecular structures and how we go from molecular structures to running calculations and doing some analysis on some of the density functional theory calculations that we'll look into. So about me, I'm a graduate student at University of Kentucky in USA. And as a part of my research, I do quantum chemistry and work a lot with Python. So the things that I've put together in these workshops are from my experience in coding in Python for chemistry. And the content is made available on YouTube. So all the workshops are made available on YouTube, and you'll be having access to the files that we'll be using. And you can always look back and see how it's done. And all the videos on YouTube are in the grand scheme of things, that how you do chemistry with Python and how you code in Python and do automation and all of that stuff. So if you want to keep in touch with all that's going on, do look at the YouTube channel where I post a lot of videos of the workshops. And about the series that we are going to start today, it'll be almost like a bi-weekly series. Today is the first session of the series wherein we will see how to generate the input for quantum chemistry calculations. We'll start with the very basics, and this assumes that you have never done anything like this before, not even generated a molecule for computational chemistry or visualized it. So this will start from the very, very basic of doing stuff. So if you are a little bit of well versed in doing all of this, you can just sit back and try to work on the notebooks that we have together. And all of these sessions will be interactive, so the files will be made available to you. You can open it in your browser. It'll be a Google Colab notebook from which you can see how we can use Python for chemistry and do quantum chemistry with Python. We'll be using RDkit. I'll tell you what that is, and then we use PySCF for running the quantum chemistry calculations. The reason for using PySCF in this tutorial, in these workshops, is it's easy to run for anyone on the infrastructure that we are using. There are other quantum chemistry softwares that are open source, like Sci4 and Orca and all of that, but it's difficult for me to actually do that in such a setting. So feel free to apply what we learn in this to other things. So the next workshop will be on the theory of DFT. So we'll first generate some molecules in this session, and then next see the results that we got from the SCF energy calculations that we are going to do today. What do they actually mean, and how we can do some more calculations like geometry optimization, frequency in the next one that will be held on August 20. It'll be from 10 a.m. Eastern time. And the last one for this series will be for calculation of absorption spectra, and how we can do some corrections like dispersion, how we can add solvents, and how we can correct for absorption spectra and all of that. So let's get started. Let me share the screen. So can everyone see my browser open? Yes. Okay, cool. So this is, I can share this link with you. And this is where what we'll be using. All the files that are needed in this workshop series will be put up here. And as I demonstrate how to do things, you can just follow along and try to do it yourself. This will be very, very interactive. workshop. You can do it yourself. And if you have any questions in between, do not hesitate to ask me in the chat, or you can unmute yourself and ask me the questions. So for today's workshop, we have the input structure file over here, the input structure for QC calculations. So you just need to click on that. And once it opens, it says open in Colab here. So you can click on this open in Colab. And it should open the environment when we're going to work. So do let me know if you're at this point, and we can proceed. And the link is in the chat. And this is the link. Do give me a thumbs up or some reaction so that I know most of you are here at this point, or do let me know in the chat. Again, for people who missed it, so you'll go to that link, go to the first notebook, and then click on open in Colab. So this will open this in Colab. So for let's start with generating structures and why do we need to do so. So if you're doing any quantum chemistry calculation, you would need a molecule in there, and that molecule needs to have particular geometry. If bonds are rotated like this, you may get different results. And if the structure is not good, it may take a lot of time to complete the calculations. So a very good initial geometry is essential for running quantum chemistry calculations. So we need to generate geometries. And there are ways in which you can do it using other graphical user interfaces, and Avogadro is one of them. Can you see my screen for Avogadro, a different screen which has a black box in between? Okay, so this is a graphical one where you can just draw something like if you just draw like this, it draws a ethane molecule, and then you can keep adding hydrogens over there and play around with this, and this is your input geometry. And some of them even give you pre-built structures. If you go to build, insert, you get fragments or smiles or all of that, and you can see there are alcohols, all of these things which you can add. You can even add fullerenes, C20, and insert. It'll add a big fullerene in there. But this is good, and you can generate structures very quickly. But if you go on creating structures like this, and it becomes a bit difficult for it to be reproducible, because every time you click, it's not the same click that you did maybe a month ago when you generated the same structure. So to be consistent with the structure generation and give you that flexibility of moving bonds around, changing the angles, or all of that, we would need to do it more programmatically using Python or some other code. So this is the reason that we are going to generate structures with Python. Okay, and what we are going to do is we need a way to represent a molecule, and we can do that with something called smiles, a smiles representation. So you can look up some details about what the smile representation is, and there's a demo over here which will tell you how you can generate smiles. And it's just like C is for carbon, add another C, it gives you ethane, propane, butane, and all of that. If you want a double bond, add a double bond in between, use a double bond. So it's a way of writing it in a characters, and we'll use this sort of representation for generating 3D structures. And you can even go to this link and see how you can just draw the structure over here, and it will give you the smiles representation on top, and then you can just copy this representation and do more stuff with it. And I'll show you how to do it in the rest of this workshop. So first thing, this is a Jupyter notebook-like environment called Google Collaboratory. And to run something, you just need to press on this play button, and you could say run away anyway, and then it'll run it. And once it is run, you'll see that it does a lot of things at the bottom. And this part of it is what we are trying to install. We're trying to install RDkit, which will help us use those smiles representation and generate 3D structures, and PySCF for running our quantum chemistry calculations. It should take less than a minute to install this package. And once it is done, you'll see a green check mark over there, and it'll show some time. And do try this and let me know if you're done with running the first cell, so that we can proceed with the generation of structures. To give me a thumbs up or any of the reactions, or you can just type in chat that you are at the step where you have run the calculation. You have installed the software. So all you would need to do is press the play button. Okay. So let's move on to the next step, which is importing some definitions. So importing definitions is these are functions that we would need to import, and this is from the RDkit library. So we'll just click on play, and it should be really quick and show you that it's imported. So this is the smiles representation for toluene, and there are various ways in which you can have this. So what I can do over here is just go to this the pubchem this link over here, and let me just do it, and draw a benzene, and then add a CH3 group on top of it, and this is the toluene. This representation is a little bit different from what I have this is the smiles representation over here. So this is a little bit different than what I have in here, but it all turns out to be the same molecule. So there are multiple ways in which you can write the smiles representation. So to generate a 2D structure, first we'll try to generate a 2D structure, and we need smiles. And the next thing would be to convert it into RDkit molecule. So we'll use the from smiles function and say chem.from smiles, and then give the smiles molecule, and it'll generate the molecule there. So if you want to visualize it, we'll use this draw thing, and it'll show you the molecule that we are generating. So this is a 2D structure generation, and you can put any smiles in here, and it'll show you the molecule that you generated. And it gives you numbers. So this is the 0 indexing for Python. Python always indexes from 0. So 0, 1, 2, 3 for all of them. And as you can see from top, we don't have hydrogens added to this molecule yet. So we can add hydrogens, and RDkit knows where to add the implicit hydrogens. So we'll use this add HS function and chem.addHS, and it'll add the molecules. And again, we'll see how the molecules with hydrogen and without the hydrogen look. So you see that we have added hydrogens in here. And right now, these are just 2D representations. They do not have any 3D coordinates to it. So if you want to look at it, we'll just convert to this mole block, and you'll see that it's RDkit 2D structure. But for running a quantum chemistry calculation, we would need a 3D coordinate like X, Y, and Z, because a molecule is a 3D molecule for us. So we would need to add the Z coordinate. So here you can see this is the X coordinate, this is the Y coordinate, and the Z coordinate is 0 for all of them. So it's just 2D. So what we do is we use this thing called embed a molecule. It'll generate a conformer of the molecule that we have, and it'll give you some 3D coordinates. And if you do this, you'll see that now we have a 3D molecule with X, Y, and Z coordinates, and Z coordinate is not 0. Okay. So any questions until here about what it looks like to generate a molecule and all of that? So we do have some exercises in between. So once we generate this molecule, we can save it, and let's see how it looks like. So I'll save it as you will use XYZ format to save it. And once you just run this cell, if you click on this files over here, you will see that there's toluene.xyz generated, because we generated this file from the coordinates that we had. So if you want to visualize it, you can download it. Let me download this. So it's downloading, and then let me open my Avogadro and open the molecule. Let's see. Avogadro. And you see, this is the toluene molecule that we generated, and it's all from smiles. And if you generate it 100 times, it's going to give you a similar molecule always. So unlike drawing it using this GUI, we have a way to generate molecules with code. So generating like a 3D structure is challenging, and it's an active area of research. So you can see this papers and links where people still work on that part. So let's go on to an exercise and try to do it yourself. The file is not downloaded. So there's a question which says the file is not downloaded after saving. If you want to download the file, you need to click on these. You should. The file is not downloaded. So the file is not actually downloaded. So once you save it, you will see that it's stored on the machine that you are running it, and this is the machine that you are running it. So you'd need to download it. So click on this 3 buttons and then download. Once it's downloading, it's saved onto the machine. It won't be automatically downloaded. You need to go to that machine and download it, because this is we are doing this in the Google Colab, and file is saved in the Google Colab, and then you can download it to your machine. So just click on this button. Okay. So we got multiple questions here. I'll start with one, and in the meantime, try generating structure for aspirin. And this is how one of the exercise. And for generating aspirin structure, what you would need to do is start with smiles for aspirin, right? So this smiles is for toluene, and you would need to generate aspirin. So look for aspirin smiles. Google search what the aspirin structure looks like. You can go on to here and then generate the aspirin molecule, copy the smiles thing, and then save, put those smiles in, set smiles equal to smiles, and do this procedure again, and see whether you can generate aspirin structure. Okay. So let me go down. Yeah. So next question is, when we have stereoisomers, the third generation, the 3D generation is random with RDkit. So the things that we generated here are random. So if you see, I'll show you later on what what 3D generation does, and it automatically adds some random coordinates to it. And every time you generate a 3D structure, it may change a little bit based on conformers. And that's what I was mentioning over here, that it's still an active area of research, and right now it's random. There are ways in which you can do it more systematically and generate stereoisomers. So I hope that helps. And the next part of it is where we are going to manipulate the structure so that it generates the stereoisomer that you need. Okay. Yeah, so there's another question. How do we get smiles for any unknown compound? So getting smiles for any unknown compound, there are multiple ways of doing it. One of the things that I would recommend is using, if you scroll up all the way to smiles, you will see that if you want a 2D, there's a link over here which says 2D structure for smiles generation. So if you click on this link, it'll take you to this page. And all you would need to do over here is draw the structure with this tool. Right? So just keep adding whatever you want to add. And on top over here, you see the smiles are being generated. So for any compound that you want, you have to draw it somewhere and then just copy whatever you see here, and these are your smiles representation. Okay. Any more questions? And do use this one, the last link that is here in creating smiles. So was anyone able to generate structure for aspirin? So that's great. So let's proceed with the next step and how we can control what we want to generate. Suppose we want to change the angle between something or distance, or make sure that it's in the right orientation and all of that. Okay. So over here, let's do, so let's use biphenyl, and biphenyl is two benzenes connected with a single bond. And over here, what we'll try to do is change the angle between the two benzenes. And this angle is called the dihedral angle. Okay. This is an example for dihedral angle. You can do the same thing for bonds, like you can elongate the bond, all of that. So let's see how we can do it. So this is the way of generating 3D molecule. So we set smiles equal to smiles, and the smiles I got from the PubChem sketch, and then we convert it into mole. And the molecule right now does not have hydrogen, so we add hydrogens as before, and convert it into 3D, save it now, and this is what it looks like. You see, so because this is a 3D representation, you see every time I generate it, it's going to change, and it's giving you me that 3D representation. You can open the initial XYZ file, you can download the file and see what the angle is, but you can see every time it's generating a different thing. I can run it again and again, and it gives me a little bit different structure, right? So we'll see how to control the angle between these two benzenes now, and that's what is mainly changing in here. If I run it like that, or like this, right? So there's a question in the chat which says, how can we draw dative bond metal ligand in RDkit? So I'm not pretty sure of metal ligand stuff, but I can search and let you know if that is something we can do in RDkit. Again, I'm not sure about this question. Sorry, I can't answer you right now. So yeah, so going back to this. So we have generated the structure, but now we'll try to constrain that angle between the bonds. So a dihedral angle contains 4 atoms connected. So if you change the the angle between the 4 atoms, we can change the dihedral angle. So over here, let me just zoom in. Okay. So we'll change the angle between 6, 7, 3, 2, I think. So if we change 7, 6, 3, 2, if we change that angle, we should be able to change the dihedral bond. Okay. So this can be done. To do this in RDkit, we have to use this, which is called which the function is called the set dihedral in degrees. So there'll be set bond in degrees or set angle in degrees if you want to change the bond or angle between something. And for that, we would need to give it a 3D conformer. And we generated a 3D structure that has a conformer in it. And we would need to give it the first argument. And then because it's a dihedral, we need 4 atom indices. So 1, 2, 3, 4 atom over here, and then the value. So yeah, and the value that we want to set. So over here, I think we are setting this angle 4, 3, 6, 11. So we'll be setting that 4, 3, 6, 11 angle, and we'll make it 90 degrees like this. Right. So this is how we are going to do it. So mol.get conformer, because it needs a conformer of it needs the 3D coordinate. So get conformer 0 will give you the first conformer in the list. You can generate multiple conformers. That's something else, but we'll just get the first one and then set it to 90 degrees. Okay. And we can save the molecule again. In this, we'll say 90.xyz and look at the molecule. And you see now the molecule is really flat like this, right? Because we set it to 90 degrees in there. So if you change this to some other value, you'll see that it changes. The initial structure may be 90 degrees or may not be 90 degrees, but by imposing this, setting the dihedral to 90 degrees, we are making sure that the output that we get is still 90 degrees. And this is what you should look like. And it's saving a 3D structure, and it's called 90 degrees. And you can see the structure generated here, download it. You can use our Avogadro to look at it. So there's an exercise now that you know how to manipulate the 3D coordinates. So this exercise is about generating cis and trans conformers of butene. So you run this is butene, and you need to this is the trans conformation, and can you generate both cis and trans conformation over here? So can use the above code, make sure that you know what to change, and we are going to change the something to make it cis and trans, right? So yeah, so give this a try. I'll give you like 5 minutes to work on this. And if you have questions in between, do shoot me questions. Or if you're stuck somewhere, you can let me know. We can work on it. And if you're able to generate it, do give me a thumbs up or let me know in the chat that you are able to generate the cis and trans structures of beauty. So there's a question which is about converting XYZ into smiles. There is a way to do it. I don't know whether it's implemented yet, but it's called XYZ to mole. And if you Google search for XYZ to mole, you'll find that function. But I don't know whether it's really implemented in RDkit, but you can just look at it. So it's called, so chem dot mole. So you can generate a mole from FASTA, mole block, mole file, PDB file, smart smiles. I don't think it's implemented in RDkit yet. It's not in there. So if you just search XYZ to mole, XYZ to mole, you will see that's code that converts RDkit thing. So there's a way how to set this up and stuff. So this is by Jensen, and he has done a lot of this, but I don't think it's right now implemented in RDkit. But you can get smiles, get your molecule from something else too if you want, and then convert it into smiles. I forgot the other part of it. So you'll be converting XYZ into molecule. So the mole part, so this is the mole. I don't know what the mole is right now. Okay, so this is the mole. And if you want to generate smiles from this, which we'll be doing in the later part, which is mole 2. So these are the things that you can do. So mole 2, we saved it as XYZ file earlier. You can save it as mole block, JSON, all of that. And there'll be something called smiles here, mole 2 smiles. So you can generate the smiles out of this mole. And then if I give the mole, I should get back the smiles. So once you generate a mole from XYZ using XYZ mole, you can convert it back to smiles using mole to smiles. I hope this helps. So yeah, were you able to get the cis and trans structures of butene? Anyone? Do give me a thumbs up and let me know if you're able to do it, or if there was any difficulty in doing it, or you encountered any error. Do let me know. Okay. So just in the interest of time, we'll proceed to the next part. And this is just copy pasting the code from top and setting the angles. So get conformer 0 and make sure that you set the angles to 0 and 180. So 0 will be your cis and the 180 will be your trans molecule. And do explore this part of it, which is allchem.set dihedral. Here we set dihedral. There are other ways of setting stuff. So if you look at chem.all chem.set. Okay, so you'll see that there's set di angle, there's angle radians or angle degrees, set bond length. So bond stereo from direction. So you can set your stereoisomers, you can set your conjugation. And we, in this case, we use the dihedral, so in degrees. So because we are giving 90 degrees, you can give it in radians. Okay. So these are some things that we do. And just pass it. So this is generating single molecule. And if you are doing a lot of computational chemistry where you want to compare things, and in some of those cases would be like, okay, I have a benzene group or something, and then I'm going to change the functional group. In that case, you would need to generate like multiple of those structures. You can do it one by one, or you can just use coding to generate it for you quickly. So the way to do that is using something called substructures. We'll not go into details of what it does, but we'll see how it actually does it, okay? And what do we need to give it. So the first thing to do is to generate the core, and we are going to substitute this core with something, okay? And usually the smiles look like this for benzene. And depending on the position where you want to add your functional group, just place a star close to it, okay? And that will tell you where the functional group is added. So the functional group will be added here where there's 0. So when you have that star placed or asterisk, you'll see that it shows up like this, and this is where we are going to change stuff. Okay. And for this exercise at the beginning, let's do it for one molecule, and then we can do a loop or something to generate multiple molecules. So we'll try to add fluorine to it. And for that, what we would need to do is, so functional group, give it a smiles for functional group, and then convert the smiles to a molecule, and this is the molecule. Because it's H, it's going to show you as HF. Okay. Once this is done, what we would need to do is we need to replace the star over here, the asterisk, with the F. So that is done with this this function over here, which says replace substructure. You need to give it a code, and then this function. This is like a representation of smarts. I'll not go into details, but these are ways in which you can break bonds and do stuff. So you need to do this and then give it the core on one side and the functional group on the other side. The functional group molecule, which you have converted from smiles to molecule, and give it over here. So once that is done, you would need to convert into smiles, because there's some detail into what is added and all of that stuff. So once you convert into smiles using mol2 smiles, just as we discussed before a little bit. So we'll convert it to mol2 smiles, and then we'll make the molecule again from smiles, so that it cleans up the little mess that it created because it tried to fix this thing. And once that is done, you'll see that new molecule now has a fluorine in there. Okay. So this is the constant thing that you're going to keep, like core on one side, functional group on the other side, and this thing in between, which will replace it, then convert it into smiles. So if you want to do it for multiple molecules, I can loop over multiple things. We'll do fluorine, chlorine, methyl group, and another chlorobenzene, I think, over here. So smiles, convert smiles into molecules. We are looping, so we'll make a list of molecules. So mole from smiles, and then we can draw the smiles. So you'll see that these are the groups that we are going to replace it with. And because we want to loop it over those product molecules, so we'll have product smiles. And because we need to convert the molecule into product, as we saw before, we place it core and functional mole, and then we'll get the smiles. So here you see that we started with benzene. We had a list of functional groups, and we end up replacing all of them. So this is a way in which you can generate multiple hundreds and thousands of structures and be consistent in generating those structures in a combinatorial way. And once you have this structure, the converting it into 3D is same as before. Right? So you have the molecule, you convert, embed the 3D structure to get the conformer, and then proceed. Okay. So there's no exercise for this, but you can try changing the molecules and try changing the functional group over here, or try changing the core part and see what it does. And a thing that I would like to mention over here is the functional group is always added onto this end. So the functional group, the core will be added to this end. So it'll be like F, and carbon is connected and not chlorine. So it always starts from this side. So whatever your core is, it's connected to this part of it. Okay. And if you want to change the position, you need to change the smiles over here. And how you want to connect. If it's a meta connection of right here, it's like yeah. If you want to connect it from phi, you will need to change it. So yeah, so you can have a list of smiles library and then just make combinations easy with this thing. Okay. So as we are closing to, yeah, so we have like 15 more minutes, but yeah, this is a good time to go into DFT calculations. So we saw how to generate a single molecule, convert it into a 3D structure. And from a 3D structure, we can put on some constraints. So we can get a very good initial geometry to start with. If your bonds are too long, or if you don't have the exact dihedral that you want to start the calculation with, it's really a pain to do DFT calculations because they won't converge. It'll take a long time to run those, and you'll end up with errors. So whatever you put into these quantum chemistry calculations, you get out. So if you put garbage in, it's going to give you garbage out. So you need to be very careful with initial geometry generation. And that's what we did so far. So for this part, we are going to use PySCF. And we'll do mostly DFT calculations in the remainder of this workshop and the sessions that follow. So we are using PySCF because it's easy to run within, oops. Yeah. So it's easy to run within this, and it should not be Sci4. So Sci4 is something that I tried, and we can't actually run it in Google Colab. So this is a thing that should be changed. But so yeah, examples. So you can see how to run multiple things, like a different type of calculations. We will go into this in the next sessions of the workshop, but you can find more useful resources in there. So at first, we'll try to import GTO and SCF, and we'll go into details of what SCF means and all of that later on. But right now, we'll just try to run a calculation, okay? So we have an input geometry because we generated toluene. So depending on what XYZs you have, you can select what you want to run. I have a XYZ for toluene, so I'll just run this. It should not be Sci4 again because this was originally done for Sci4 and I had to change it last night because it stopped working. So we'll import it to PySCF. So this has gone into PySCF now. So from PySCF generates a molecule. And then these are the functions that we need. These are some of the details. The details of these parameters will be discussed in the next session. It's called basis set. We need to set some basis set, some functional, and these are called exchange correlations functions. We'll deal into that next time we do it. But if you want to run quantum chemistry calculation, you don't need to really know what quantum chemistry is actually doing. All you need to know is how good you can code it and run the calculation. So right now we'll do that. We'll assume that these parameters are perfectly fine for us and they give what we need. So set the parameters, and to run the calculation, it's mf.kernel. And the more details on how to do it, you can find it in the tutorial here or there. But once we run it, what we are going to get is the total energy of the system. And the value that you see over here is in Hartrees. Hartrees is an atomic unit for energy. And this is the energy for toluene when calculated with this functional and that basis set. Okay, so if you are up to here, you have successfully run a quantum chemistry calculation for toluene. So yeah, so there's a question in the chat which is about are these PySCF results comparable and acceptable to that of Gaussian or quantum chemistry calculation should give you because it's a quantum chemistry calculation. You have some similar. The basis set will, there's a list of basis set repositories, and functional is the same functional. They should give you very similar results, and it should not be drastically different. What is different? What changes between the softwares is how fast they run it, what algorithms they use in between to speed up the calculations. So if you use something more commercial, it may be very, very fast. Something open source may not be well optimized uh, for for the architecture that you're using. So it may take twice as long to do it if it's not well optimized. But the results should be pretty much comparable if you use the same basis set, same functional, and other parameters that you're going to use. So there's an exercise now. So this is about doing SCF energy calculation. So generate a molecule. You have already generated cis butene and trans butene. So what you can do over here is try to compare which one of them is more stable, whether cis or trans. So the more negative value will be the one which is more stable. So try running these calculations for cis and trans and see which one is more stable, because you get total energy from them. And this is your start of running quantum chemistry calculations. And we'll spend like 5 minutes on this. It's how much? Yeah. So we are close. We have like 10 minutes. So we'll spend some 5 minutes on this. And if you have any questions, you can let me know. And there's a survey at the end so that you can give me some feedback on things that you would want to know or things that can be improved. So do fill out the survey and let me know your thoughts. We're still here for 5. How do we get optimized structure? So there's a question which asks, how do we get the optimized structure after SCF calculation? So I'll talk about this in detail the next session, but just to give you an idea of what's going on here is we have generated a 3D geometry, and the geometry is based on the random conformer that RDkit generated for us. There are ways in which you can refine the molecule a little bit, and we saw the manipulation of it. Over here, what we are not trying to do when we calculate energy is try to minimize the coordinates. So we are not trying to, if the bond is too short, we are not trying to make it optimal. We are not trying to move the atoms to make the bond have optimal bond length. Over here, what we do is give it a structure and calculate the energy of the structure. And for that, we are not going to do any optimization right now. And these are called self-consistent calculation, where we only calculate energy. We are going to solve something called Consham equations, which give you energy for that particular state. So we are not optimizing it. If you want to make sure that all the bond distances and bond lengths are optimal, we would need to take derivatives of the energy that we get so that we can minimize something. And that's the optimization calculation for the structure. And we would talk in greater details about how to do optimization of the structure in the next session. Right now, it's just the structure that you put in. It's the energy for that structure, not the optimized structure. I hope that helps. Cool. So any other questions? Was anyone able to find out which is more stable, cis or trans, from the structure that you've generated? And you can try messing around a little bit here. You can change the functional and see what how much of a difference does that make. If you go to this tutorial over here, you can see the functional that we're going to use. I should have linked my bad. So if you go to this page and then go to DFT, and go to simple DFT. And this is where some of the code we can get from. So we are using B3lib right now with different basis set. So these are the other functionals that you can use and try to see which one gives a better result. Which one is able to distinguish better between the cis and trans. So there is a question, could not get the structure from cis, says the molecule object has no attribute percentage key. So I think such errors occur if the smiles, something went wrong with the generation of the smiles, or you did not have, I think, could not generate the structure, it says. So I'm not sure. Maybe you need to create a molecule and then have a 3 mole as an object attribute percent as key. I think maybe the 3D coordinates are missing in there. That's creating that problem. So you need to, if you remember, I can just scroll up and let's see where it is. So you would need to embed the molecule. I think the embedding is missing into it. So you can try doing this part and see whether you can generate it. I'm not sure whether that actually helps. Or is it the PySCF that you're talking about? I think it's the PySCF. As long as the structure, you can visualize it. Again, visualization is very, very critical. So before running any calculation, make sure you download the stuff. So if I want the 90-degree, I download it and then visualize it with my software. Is that? Yeah. So I visualize it. So this does look 90-degree, and in Avogadro you can do the measurements using this thing over here which says click to measure, and I can measure, click on 4 atoms and see whether it's 90. Let's see, it's 90.1. It's okay as long as it's 90, close to 90. So it shows you the angle, the dihedral, and the distances between 1, 2, and 3 nodes. So do check whether it's the right XYZ, and sometimes that could be the error. I think mole objects is probably the PySCF thing. So it failed to, the saving of the coordinates may have failed, or hydrogen's missing. I'm not sure. I've never seen that ever before. Oh, cool. That's cool. So again, initial generation of geometry is very critical. So if your initial geometry is not good, things fail, and it's really a pain. Okay, so we are to the close of the session. So we'll continue this on like 2 weeks from now, same time, 10 a.m., where we'll discuss how to optimize the molecule. Right now, we just used energy, used the geometry and found out the energy of that molecule. So in next, we'll discuss about how to generate, how to optimize the molecule, and how do we know it's really optimized, and look at some details of what these actually mean, and how do we know what to use and what not to use, like what is the basis set, what is the functional, and what do you mean by SCF energy, and how do we come up with this energy value. So we'll get into some details into it and see what is the reason for using the things that we use. Because in quantum chemistry, there are hundreds and thousands of basis sets, hundreds and thousands of functionals, and the thing that chemistry comes in is how to use it, and which is the right functional or right basis set for your system. The rest all of it, as you saw over here, even if you didn't have any idea of running a quantum chemistry calculation or did not have insights into quantum chemistry or basic knowledge of quantum chemistry, you are still able to run a calculation over here. But chemistry is where you come up with the knowledge of why you use the basis sets and stuff. Okay. So next time we'll discuss a little bit of theory about it, and then move on to how to do optimizations and what we actually do in optimizations. So it'll be a little bit theoretical thing, and I'll tell you in not in glory details of what it is, but something that is good enough for you to understand and proceed with doing such calculations on your own. So yeah, I'll stop the video.